Okay, here we go for week 4, PLC2, remote I/O. So it's going to be kind of a fun one right here because up to now all we've done is local I/O. So it's going to be fun to do remote I/O. And so once again, I want to say welcome. This is recorded, so I just kind of take a look at my YouTube channel and see how many views we had. Hopefully you're watching this and get an idea what's going back. I got past back papers here. I've been grading stuff as we go. I've got a couple people with a few labs still out that they're working through and finalizing. That's fine. I say right here, how's life? I think everybody's in a reasonably good spot. I just want to remind you right here on it when I say how's life. If you don't get the labs done, you might want to turn in what you have. Just be sure that you understand, what we learn when it's all said and done. I said you can go back later and maybe try and find some time to get those done or not. I don't know, but don't get caught up and get behind. So so far so good. I think everybody's okay. Just wanted to throw this out there. We did talk about the anti-tie down and the one shot and stuff like that. I don't know if you watched that video from last time, but to reiterate, that video is right here if you want to watch some anti-tie down solutions and one shots and some weird things that happen with the scanning of the controller. Watch that. I got scheduling example right here, and so what I've got going is I think I told you, many of you, is that I like to buy and refurbish industrial automation equipment. A lot of times I buy controllers, old PLCs, new PLCs, whatever, and refurbish them and then I sell them. That's my little thing that I like to do. And I just recently got a SLC 505 processor, which is an Ethernet processor for the SLC 500. And when I get that, I like to kind of upload the program and see what it is. And so I did that. I uploaded this. Oh, I might be at the wrong one. Oh, maybe this is the right one. No, this is not the right one. Let me just pull this up real quick and then. Okay, here's the program that I had pulled up on that processor. And so you notice right here in the SLC 500 looks a little bit different. Here's all my subroutines right here, and my ladder 2 would be where I would be starting to schedule stuff. And so if you go into here in this ladder 2, well, yeah, there's some ladder logic with some moves and everything, and you start looking at this and trying to figure out, hey, what is going on here? And you start moving down here, and here's where the scheduling is starting to occur. And so here's my JSRs where they're scheduling, and this one here is unconditionally scheduled. These ones are unconditionally scheduled. These ones right here are conditionally scheduled, and this bit B310, whatever it is scheduling these other subroutines. Now, I don't know what that is, and I'm just looking at this and I'm thinking, like, man, what if I had to troubleshoot this? I don't know. Let's go into ladder 3. So ladder 3's got some compute, some moves. There's more computes. There's greater thans. There's some inputs. So there is no run comments here. There is no descriptions of what any of this is. There's certainly conditional and unconditional scheduling of these subroutines, but this is going to be gnarly if you have to come in here and try and troubleshoot and figure out what is going on with this processor. And you can see that there's just no matter what subroutine I pick, there's just tons and tons of stuff going on here, and I just want to encourage you once again to try and put on run comments, try and pick tag names that are useful. Tons of files here, it's crazy. And the I/O configuration for this one right here, what this did is it had a DeviceNet scanner module, and that's what we're doing. And it had normally relay output cards and input cards and all this. Analog cards we'll do later, but it had a DeviceNet scanner module in it, and that is what we're going to be working with a little bit, because that's a remote I/O. And if you go into your your inputs, your outputs right here, you can see that DeviceNet scanner module that's in slot 1. Look at all the data that comes with this thing. I'm still in slot 1 over here, and I'm on the 16th word right here. Here's the 17th word. It just keeps going, right? And then finally up to 31, and then finally here's the normal output card. Here's the normal output card. Here's the normal output card. These have 16 bits, but these DeviceNet has got 31 or 32 because we started 0. 32 times 16 bits. That's the amount of I/O that's coming in on this DeviceNet remote I/O, and we'll be getting into that a little bit, but there's going to be an incredible amount of I/O coming in, and this looks like it's hard to find here on a SLC 500. When you get into Logix and you put this in, drilling down into the controller tags is going to be brutal. You got to really understand what you're looking for on the left here when it talks about, your reverse I/O. So I thought this was kind of a nice segue, because this does have on my I/O configuration a DeviceNet scanner module, and we'll be doing DeviceNet, and we'll be doing remote Ethernet IP. Okay, so those are a couple of housekeeping things. Let's take a look at the lab review. Now, most of this is going to be kind of the lab review. I want to be sure you understand and that you can do well on the quiz. On the quiz, by the way, there's an item that you have to fill out for me, and so later on in the PowerPoint, there is, this page here that if you want to download this ahead of time out of the PowerPoint so that you can use this for the quiz, that's what you're going to need. That's what you're going to need for that last one, okay? And I'll talk about it again when I get there. So, mixing up the push buttons and toggles, you really had a lot going on. A lot of push button, lots of toggles, a lot of scheduling, unscheduling. Just be sure you know what's going on. And then you were using, outputs. You're using things multiple times. And so just have a good I/O map so you know what's going on. On your outputs, you can use an output more than once. You just went and you used light 1 like 3 times, but then you unscheduled it, so you weren't really using it. But your program kept giving you warnings when it downloads, says, hey, we're using output more than once. Well, yeah, it doesn't like that. And so just be aware that you probably don't want to do that in real life. You just want to use an output once. You don't want to use it multiple times. I got italicized here, not understanding examples before trying to program the application. So I gave you these little one-hitters where you just went in there and you answered the questions. And I just want to caution you, just don't answer the questions and turn it in. Try and understand what you were learning there, because then, boom, I bombed you with those harder ones, and some people got bogged down. But it seems like everybody kind of got in the groove after a while, like, holy moly, I better see what's going on here. But the moral of the story was there's big differences in retentive versus non-retentive and non-scanned, and I'm going to go over these. And this can burn you in your scheduling, because you'll be like, something might be scanned or not scanned, and a light might be on or not on, and you've been trying to figure out, what the heck, why is this on? So that was kind of the moral of the story for lab reviews. I really wanted you to understand the downfalls of scheduling that might get you in trouble. And so pretty good problem solving on activities. And I remind you, it's going to get hard. You're going to have to really problem solve and get through some of these activities. So output modules are sourced, input modules are sunk, and they're often run through a safety relay. And another thing I got here, you need to know how to read the connection diagram, because I'm giving you all these schematics, and people are just kind of like plucking wires in all over. Man, try and get yourself a connection diagram. So it says output modules are sourced, input modules are sunk, and they're often run through a safety relay. So when I'm looking at my safety relay right here, remember it's mostly these 3 contacts right here, these redundant contacts that are closing. And so that's where you want to try and control your output. So the different ways, once again, were to take my voltage and pass it through some contacts, and then this could go to, the output module, the voltage on the output module, okay? And at that point, all the devices on the output module come down, because we're killing the voltage to the output module through the safety relay. That's one way to do it. The other way would be if you just had a single output, once again, your voltage would come in here, and then this would just go to, a single load. Let's say you had a motor starter or something like that, and it would just bring this motor starter down if it was coming through. So somehow these contacts have to bring down the controller of the output, and the controller could be the motor starter, it could be the PLC output module or something like that, right? And then the other thing was, you were taking these other ones, and then you were running your sync, or you're running voltage, sorry, into the input module, okay, like channel 1 or whatever. And so you were monitoring the safety relay. Notice these are not double or redundant contacts and all that kind of stuff, because they're just monitoring, and you were using the status of this to affect your PLC program. But the PLC program is all fictional. This right here and these right here are real. That's why we're running them through these contacts and bringing them down. So hopefully, you're getting the gist of that as you go through and you're hooking these things up. Okay. So the MCR versus the safety relay, and so the safety relay can be used to replace the MCR contact. So this diagram is kind of what I was showing it. And in the past, what we did is we had a CRM, and they got CRM too, but this could have been CRM1 that we had to bring the master control relay on, and then boom, all of a sudden the input module's working and the output module working and all the field devices if the master control relay was on. So this is emergency stop switches. We're thinking about a stop switch, which has a single set of contacts, but now we're thinking about an emergency stop or a safety gate or something like that has redundant contacts, and they can be put in series with other safety gates and other safety relays and other light currents, a whole big safety circuit. So, this whole thing right here, now the emergency stop, this could really be just replaced, if you're thinking about it, by a set of contacts right here, or multiple sets of contacts, and it could be just the safety relay or the dual channel safety, whatever form that takes. Okay, and so that safety relay could bring down the MCR, which brings all this down, or the safety relay can replace the MCR contact, so we could still have the MCR contact, which we know we could use for some stuff here. It could still be here, or we could put another set of contacts right here, which would be the safety relay contacts. This one right here could be the safety relay contacts, 13 and 14, and that would be the MCR. And then we have the safety relay contacts here, could be 23 and 24 right there, right? That's really getting redundant. Or we talked about bringing an individual device down. If we just had one device, like this one was really dangerous right here, we could have put our safety relay contacts right here to bring that device down. And that could have been, 33 and 34. Now, what I've done is I've really overkilled everything. I've used this safety relay, whatever it takes to reset this safety relay, which would be, S11 and S12 is one channel that needs to get reset, and S21 and S22, or call it cleared, has to get cleared. And then, yeah, this is my reset here. But these have to get cleared and closed, right? And I don't know if you have monitoring or not, without maybe no monitoring. But I've overkilled this. I've got the safety relay bringing down the master control relay, which is in series with the same safety relay, which would come down, and then the safety relay, if it comes down, is bringing down output like that. This is way too much. Like, you don't need to do all this. It would be kind of be like one or the other. Sourcing the output module, not killing the source of the output module or killing the device. This is just way overkill here. Hopefully, any one of these techniques you understand and is going to help you bring down the controller that brings down the field device. All right. So we did the master control reset instruction, and this is similar to kind of like adding a bit to start each run. And kind of, it's really just like killing the power of it, almost like a master control relay. And I said, don't ever use this. I don't think this should ever be used. It's a really weird instruction. It was made to replicate a master control relay. So normally we had, a master control relay here. I just showed you, or safety relay, whatever. So when this opens, this whole rung of voltage goes bye-bye. That's kind of what it's simulating a master control relay. Well, that just means that if this toggle is on right here, then between the fence here, or the zone, all the voltage is gone. Well, so that means that if you hit this toggle 1 MCR, whether these were held or not, this went off, this went off, this went off, everything just goes off, because it's almost like it doesn't have any voltage to it. And then when you flick it back on, well, if this toggle was made, the light comes back on. This was latched, so it's almost like that 2-coil latching relay that would come back on. This one right here, it doesn't come back on because it treats it just like a magnetic dropout where, you lost your magnetic dropout. And so, the MCR, you needed to take a look at the program and say, okay, I'm pushing these buttons and then I kill all the power to it. And it's working just like something would be if I hardwired it and somebody killed the power to it. Okay, that's kind of what this MCR example was doing. It's like adding a bit, not really. It's a little bit of schedule. Retentive output stay on. You have to think to identify the fenced operations. Why is it hard to troubleshoot? Because if you have multiple MCR instructions, it's like later on here you got an MCR going through all kinds of stuff, and you got an MCR going through all kinds of stuff, and you got all these MCRs. Notice this doesn't have a name. This does not have a tag name like zone 1 or zone 1, and then you would know that they were, and then these would be zone 2s. It's just the MCR, and they were coming green. So if you have these MCRs and somehow you confused it and you thought the zone was from here to here, and there was a zone within a zone, you would have a hard time trying to figure out exactly what was going on here. So that's why I recommend, you're not really going to use this. You're going to see it in you can go on forums like, yeah, I saw that in my my college PLC class, and then we never saw it again. I'm like, yep, I think so. But it's interesting to think about the retentive nature of it. The next one we did was the jump to label. Let's see if I got that one floating around here somewhere. A jump to label. So when it deactivates the logic, which could save some scan time. We talked that the scan time on these processors is pretty impressive. They can really pound it out. But I just showed you that 6500 one. There was a lot of logic there. I showed you the zones down and the flex downstairs. There's a lot of stuff going on there, right? But remember, outputs stay in the last state. How often do you want the outputs to be in their last state? So if you're jumping to a label, you'd think that you were doing that because you didn't want that logic to execute, and so you think you don't want the outputs to be in the last state, but maybe you do. It's something that you really want to think about, and that's what this was when this jumped, it jumped over all of this. And remember, you needed a no op here, right? Because it needed to be cleaned up on the end. And so if this light was on and these lights were on, well, when you jumped, you still had some retentive issues that you were dealing with. It was not treating it as a magnetic dropout, depending on if you were jumping in using outputs or using bits. So this one was getting, a little more complicated. And to tell you the truth, I don't use jump label really that much. Usually I would just use JSRs. Most of all this stuff can be accomplished using JSRs. But another thing I don't do is I don't typically do a lot of conditionally scheduling of JSRs. And if that's what you don't want to do, then boom, the jump label might become important. It might become useful. All right. So there's my jump to subroutine. When true, it activates the logic. Outputs stay in the last state. So if you're doing conditional scheduling of a JSR, then you're back to the same thing. Like, how often do you want those outputs to be into their last state? You're jumping out of the subroutine. And so that was, like I said, you're just going to see a lot of, JSR, JSR, just a lot of unconditionally scheduling. And then you don't really need to worry about, that you unscheduled something and then the output was in the last state. But the minute you put, some type of a condition on here to schedule that subroutine, and, a lot of times we talked about, doing a toggle switch and then interlocking it with a toggle switch. So you're calling one or the other, let's say. Be careful, because you're going to get some retentive nature by unscheduling it, and it's going to kind of get you. So I don't do a lot of conditional scheduling of JSRs for that reason, but sometimes you gotta, right? The input output parameters one was just a great one. That really made you think, right? We programmed just moving like a dent in and out of the subroutine. we brought in a number, used that value in the sub, and then we pushed something back out to the main. It could be more powerful if we start using analog information in and out of there. And then often we need like a zero situation to reset the parameters. And that was what we were talking about here. You know, we had these interlocked right here. So, hey, if we were not pushing a 1 or a 2 or a 3 into the sub for being used, then automatically just push a 0 into the sub. So, and then we did some counters and timers with that, and we pushed because we wanted the timers to reset if we weren't doing any of this right. Otherwise, what we were having happen is we were using a push button to push a timer value in there. Okay, so we had a push button, and it was a JSR, right? And we pushed like 1,000 into there for the timer. Or this push button was a JSR, and that pushed like 2,000 into there, right? Well, the problem was, if we push this and it started timing, and let's say time and it was at 1518, so it wasn't there yet, and I let go of the button, it unscheduled it. It unscheduled this, at which point it kept the value of the timer. The timer is no longer being scanned, but it keeps the value of the timer, and therefore, if we were using the timer timing bit, it doesn't see it as being done, and the light is still on. So what we had to do was we had to interlock this, you know, with these two buttons right here, so that, you know, JSR, we had to push a 0 in there. So if I wasn't pushing if I wasn't pushing these, then it reset the timer so that it wouldn't get caught on a number when I let go of this and unscheduled it and kept the retentive nature of the timers and kept the retentive nature of the outputs and everything like that. So that was cool. I hope that you saw that was the problem and how it worked. And here's the same thing. Once we're in the sub, the return parameter is paint status. And we were using the return parameter paint status here. Now, here's another thing I want you to be sure. The return parameter paint status doesn't need to match the name of the tag in the subroutine. That's what some people were worried about. The subroutine tag that you said the return parameter in the sub could have been called Dorito. Well, that tag Dorito in the sub gets brought in and it gets renamed as paint status in the main, and that's what we're doing. So some people were struggling a little bit with that. You know, you just say what that return parameter is going to, with that return parameter is now going to be called in the main, and it doesn't need to be called paint status. All right. So what you can conditional schedule on subroutines may not be a good idea because the retentive nature could be confusing. Certainly, you're going to see it out there, and you might just have to do it, and hopefully it works for you. Other AFI input kills a rung would not be used. So, you know, you're going to have just a ton of subroutines and stuff. Maybe you want to inhibit them or something. An AFI is almost like inhibiting that subroutine from the main, but no op, you need that. Along these lines, don't do this. I had one student, I think last year, he put all of his programs for the entire semester all on one program, and he just AFI'd all the subs. He had like 500 subs in there. He had like 2,000 tags. I mean, it was this crazy for him to keep. I mean, he was able to keep track of it, but I recommend just starting over once in a while and not just have all these subroutines that you've AFI'd, because you're just going to get so many tags, controller tags and local tags. It's going to be messed up. So the one shot, we talked about the one shot last time just a little bit. I asked you to watch the video. It's there again. If you need to watch this video, it shows you how you can use one shot. It's kind of like a flip-flop. And also that the one up here that I showed you for the timer, the anti-tie down, I think I threw a one shot in there to talk to you about some of those. So you want to take a look at the one shot because you'll be using it a little bit, and I just can't tell you when. And everybody won't be using it the same because all you are coming up with different programs. There is no single solution for this. And once you program yourself into a corner and your scan is not working like what you want it to, you might need a one shot. But somebody else might have programmed it differently where they don't need a one shot. So you want to take a look at that video and be sure you understand how it works. Safety gate switch. There's lots of different ways this is used. Did you check the operation of the safety gate circuit handed out in lab? So in the lab, I kind of started by just breaking down a complicated safety gate switch, and it showed you the connection diagram of a safety gate application, and it might have been Omron, even though we're using Allen Bradley. Well, they're just diagrams. You got to learn how to read these diagrams and take a look at them. And so, you know, on the safety gate with the relay, the thing to remember is that we're using the relay, the safety relay, the redundant contacts right here to, these are what are bringing down the field device. So this exists for a reason. If we're going to bring down S11 and S12, that channel, this is channel 1, and if we're going to bring down channel 2, if we're going to bring those down, then we have to use the relay to kill the device right here. This right here, you know, one's going to voltage and one's going to my device. That's the purpose of the relay. This and the e-stops and everything like that are just means to bring the relay down. So on this, you know, you were basically taking S11 and you were running it through an e-stop, right? And then you were running it through probably like a contact up here, okay? And then you were maybe bringing it back this way. So this ran through 1, 2 contacts that were in series. And because that e-stop is a dual channel e-stop, these are together. This is the same e-stop right here. It's just got 2 channels. And then same thing, this thing ran through this one and then back to there. So, you know, the diagram gets a little messy here, but really what you're seeing is S11 is running through the e-stop contact, it's running through the safety relay contact, and then it's running back to S12. And then S21, so S21 is running through the same contacts back to S22. So these right here are your e-stop, and these right here are my safety gate, right? And you're like, well, what do I need? What if we want 2 e-stops? Well, you know, you're just putting another e-stop in here somewhere, another dual channel e-stop right here, and they're going to be in series, and they just get added, you know, I don't know, add it right here if you want. Put another e-stop right here, and then that's really the same e-stop here. I know it's getting a little messy, but these are the same e-stops that get pushed. Or you put another safety relay in here. You put like 50 contacts in there if you want. But then when this goes down, it breaks the good contacts, the DCS contacts. And then, you know, the wiring here, like I said, you know, what were you doing with this output module voltage here for your devices? Some people were taking my voltage, bringing it through the good contacts, and running it to my output module. All right, that's my voltage. Well, if that's the case, then when this safety relay goes down, this whole module goes down. That's pretty safe. Or, like I said, some people were using it to just bring down the light. We had a light, I think, is what we were doing. We had a light that we were bringing down. Either way, you know, you could do it this way, or you could do it this way. You know, you're running out of here just to the light, or are you running out of here? That's what this is, through the safety relay to the light. You know, that's what this one is here. Either one is the same. And same thing on the input here. You were taking some of these contacts here, some of these contacts, these 41s and 51s, and those were running into here. You know, one of these contacts could have been the safety relay monitoring contact, 4142. One of these could have been the solenoid contact, 4142. One of these could have been the key lock, 4142. So at this point, this input knows if the safety relay's been reset. This input knows if it's been locked. This one knows if it's been closed. You know, so you can use these monitoring contacts, which are usually, you know, like I said, 41 and 42 are good examples of these devices to monitor it. And so hopefully we've been doing a lot with these safety relays, and you're kind of getting the gist of it. Okay. Now this is the item here that you might want to print off for the quiz, or when we get to the quiz, you might just want to upload or download the PowerPoint so that you have this in front of your face, so that if you need to kind of draw this by hand, you can. or if I gave this out, there's an extra one. If there's an extra one of these in your notebook, then that's what you want to use, when you're doing the quiz and stuff, right? So on the part E, there was lots of variations for that. I didn't care. What I'm going to show you is craziness. All right. I'm like, man, I'm just going to have fun with this. All right. And I created the last part with a blinking light, just having fun and just being crazy. I don't want to see anything like this turned in, because then I know that you just copied what I turned in. But I was just having fun with it. Okay. And so the first thing I want to talk about is my scheduling. And like I said, I was doing with the selectors, which is just kind of fun with one or two, so that I was either using a JSR to get the blinking light. I did another one where I used jump label to get the blinking light. I did one where I used the MCR to do it in the MCR safety. So I was just kind of having fun with my scheduling here to call only one of these subs at a time. And in my playtime here, I did use an output more than once. You wouldn't want to do this, but I was just having fun. And so what do I got here? I'm going to take a look at my paper here. So, this was the first one. That was my scheduling, and here were all my subroutines, just kind of having fun with it. My first one was a JSR option. I used a jump to subroutine, and I interlocked it with 14. Okay, so I was either calling this subroutine or this subroutine, auto or manual. Okay. And so it was kind of like a jog circuit. And so when you're thinking, oh, it's like a jog circuit, it's kind of like what we learned in 131, right? When you learned in 131 that you had a stop, and then you had, a run, I guess, or an on, I don't know what you want to call it. And then you had a control relay, and then you had like a selector switch, and then you had a control relay here. And so this was run jog. So if you click this one way, you kind of turn the memory on to the control relay. And if you clicked it the other way, you turn that memory off. So by pushing this button, you could either get it to run and then it would go off, or you click it back the other way and it jogs. This was kind of the basic run jog circuit that we had. Well, this wasn't totally going to work for my JSRs. What I did was I basically put in, I put in my safety. I'll call it safety relay. But remember, I could have had, a bunch of safety relays. I didn't use all these safety relays, but I'm just overkilling it to say that you could have all these safety relays, right? And then if I pushed the on button, I was going to get what I called it, some type of a bit to come on, let's call it manual. I was getting a manual situation, all right? Versus in the other subroutine, same thing, I would have all these, safety stuff going on, whatever my safety circuit here. And on this one, when I pushed on, I was getting an auto and I was getting memory with the auto, okay? So I was either calling this sub, which didn't have any memory, or I was calling this sub, which had memory. And so what I did, because I didn't want to use an output more than once, I returned this subroutine bit to the main, and I returned this subroutine bit to the main. And that way I only had used the blinking light once, because this was going to be true if I was in auto mode. If I was in auto mode, I would just push this button and walk away. It would just blink, 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 blink. Or if I hit the selector switch and I scheduled the other subroutine, I would get the manual bit to come on, okay? And so my JSR, here's my auto subroutine I was talking about. And here I had, I said safety relay, whatever my safety circuit was. And that's all that I'm showing here, is that I had, it was the gate key, the gate was toggled, the switch solenoid was on. And here was my big circuit. Basically, I was in auto, the gate was closed, the gate was locked, the gate was toggled. And then if I hit start, I got memory, okay? And then that would return it, okay? And if I had the memory, I was basically, blinking my light here, my cascading light. But I wasn't really blinking my light. I was blinking a bit, okay? I was blinking a bit there. That's what I was doing. I was blinking a bit. And then in my main, that bit was blink, blink, blink to blink the light. So I only had to use the light once. Or if I unscheduled this and scheduled this, the manual subroutine was very similar. You know, I could still have all my safeties and everything like that, my timers and everything like that. But you know, what I would have is I would just blink the manual bit, okay? And so, you know, the same thing, you know, I would put all these gate lock and something into here, and then I would just get a bit that was a manual blinking bit. Notice memory. Notice there's no memory on this one down here. So that's kind of what I had going for a jump to subroutine. Got to be careful that if you have this memory and you jump out and jump back in, does this memory automatically come back on? You know, there's things to think about the retentive nature. Jump to label. Once again, I was just having fun here. And here I have a blinking light bit A or blinking light bit B. And one of these is going to have memory and one of them is not going to have memory. And there's my blinking light. That way I only have to use the light once. Either this one's going to be blinking and it's going to be, you know, in auto mode, or I'm doing this one blinking and it's going to be in manual mode. So I used here's my cascading circuit right here. So here's a jump label, auto end. There's one jump, and here's another jump here, okay? And so you see I got 14 again here, manual toggle. So I'm either jumping over the automatic function of it, or because they're interlocked, one's closed and one's open, or I'm jumping over the manual. So I'm either jumping auto or I'm jumping manual, so it's only going to be in one mode. If I'm jumping over manual, that means that I'm running this one, and guess what? That's got the memory circuit on it. Or if I click it and I jump over this one, then I'm actually running this one, and notice there's no memory in it. So same thing, I got, you know, this is just my safety circuit. It's on, key, gate lock, gate toggle, safety, reset, just do what you want, and then return the blinking light A, or return this blinking light B. One of them is held on with memory, one of them isn't. These are in the PowerPoint if you want to study them and say, man, that's crazy. You know, why did you do it? I mean, it works. You know, I was just having fun. My master control relay options. I said, all right, let's do a master control relay. So what do I got here? I have start, and I've got blinking bit, and notice I've got like an auto memory thing here. So this is now looking like that 131 circuit, you know, that I kind of drew here, right here, where we're kind of, you know, oh, sorry, right here is kind of turning that off and on or not. Here's my blinking circuit. There's my blinking light. I only need to use the blinking light once here, because my MCR zone right here is if I do my auto manual toggle right here, I am going to be jumping over this circuit right here. It's auto memory, and there's all that. So basically, if I'm jumping over this, when I hit start, this whole thing is dead because I've jumped over it. And so start is going to blink. It's going to blink this bit, right? Or if I turn the MCR back off, I'm calling this, and when I hit start, here's start right here, and here's start right here. I hit start, I get auto memory. That's my little memory bit, similar to what, you know, we had right here. And then boom, it will blink. All right. So that was using the MCR. And then on here, you can take a look at this. I just got a little crazy because I wanted to get my MCR retentive with safety. That was me just throwing in all the whatever safety conditions you want. Was it toggled into auto? Was the gate key on? Was the gate key shut? Was the solenoid on? Was whatever, you know, that was the condition that you had to have, you know, the memory right there. Okay. And so take a look at these if you want. These are and I did them, I know, but I fancy a very creative way to blink a light using different scheduling options. How would I do it? I would probably just condition, you know, I probably I probably wouldn't get too fancy with the scheduling. I would probably try and create, something in a main program similar to what we learned in 131. Um, trying not to get an accidental retentive nature of the subroutine, going. Okay, so this was super fancy. It's certainly overkill, all of these, and a lot of you just did keep it way more simpler, and I was fine because I just wanted to be sure that you understood that you could do something here like this, and then get it going. Okay, so those are all here. I got them here, and you can dig into what I showed you and take a look. We did the subroutine parameters, passing stuff in and out of the light bit. That was getting a little more tricky. I'll show you something here in a minute related to passing that in. We talked about it. A couple things you can't delete. Tag, maybe you've made that tag a controller tag and you're having a hard time getting rid of it. A lot of times you have to go offline then and do some stuff. Tag type references the controller, so we're doing you right now. We're not using a lot of controller tags other than what's coming with the IO. Using a lot of local tags. This can be done with controller tags, and the farther you get along on the different versions of logics, there's a lot more tendency to use controller tags. Your tag Dorito, well, that could be a local tag, or that could be a controller tag. If it's a bit, maybe it's better as a local tag, and if it's an alias for an IO, maybe it's better as a controller tag. I don't know. I got my homework review. Group 1. While checking the operation of the parts tracking system while monitoring the tags in a window, you note that the value of conveyor sensor 1 remains high. So, you're checking it, the tag in the tag window. You can check it online. And so my best guess here is I'm going to start with the sensor to see if it's bad, or if it's clogged or not reading, something like that. Because typically, when something goes wrong, the first thing you're not going to do is jump into the PLC program. If it was working fine before, there's probably a problem with your field device. This is steps needed to search. We did that. I showed you how to search something on the flex. A single pole switch is used to variable preset timer. So basically the best way to do this, and what a lot of people did, was they just did a move on the timer. So they had an interlock right here, like this, and that was the selector switch 1. And so you were doing one or the other. And so you did a move, and you did a move, and then this move, I don't know, what was the values on that? Let me look at this again. For 10 seconds or 15 seconds. So you were doing 10 seconds or 15 seconds into the timer preset. So that's kind of the way most people did it. They just had it interlocked. But once again, just because I'm playing devil's advocate here, I don't know if you want to do this or not. If you wanted to overkill, you could use a JSR with an input parameter, so that if you pushed a button, it moved that value into the timer. Or if you push this one, it wouldn't. They could be the same button interlocked. It would move the 10 seconds into the timer, or the 15 seconds to the timer. That's kind of what we did, similar to the lab. This is overkill. You didn't need to do it. It was fine. Quiz review. So the quiz review was okay for the timer structure. Which member indicates it's equal to the preset value? That's when it gets done, when the timer's getting done. The timer tag name for the above is solenoid delay. That's it. This is just nice. You can put this other information on here, as a description to help you identify it. I just showed you that slip 500 where there's no information. Which instruction can best be used to turn an output coil on or off after the run has been true? Probably a TON for a desired amount of time. You want to time on. A repetitive delay timer, the run goes false, it'll keep the value. The processor is placed in run mode. The power is temporarily interrupted. Yeah, you just unplug it, turn it back on, and it's going to keep the value. The counter counts false to true. So you push the button is when it counts. The counter accumulation is reset by a reset instruction. So you do need RES instructions with the same name, just like we did before. The second row is not going to verify. And the issue is right here This is a contact. A contact is on or off, so it needs to be a Boolean data type. A test counter.acc is going to be a dint. So a dint is 1, 2, 3, 4, 5, 6, 7, all the way up to 2.2 billion, and that is not on or off. Okay, needs to be a Boolean. Which description best describes a safety relay? A safety relay is wired to directly control the machine control circuit. You want to bring that down. Necessary connections that can so an ESAP can manually operate an electric motor circuit include output monitoring. So I guess I'll put one together here for you real quick. Hang on. So let me see what we want. We got an E-stop and we got a reset. So you can manually operate include output monitoring. Okay, let's see if I can work on it. Pretty simple. You had, line 1 powering this up, line 2 powering it up. You wanted a dual channel E-stop, and that's where we're going to put, our E-stop right here and our E-stop right here. There's our dual channel E-stop. If you wanted to have 2 E-stops, it didn't say it, but you could have a 2-station E-stop if you wanted to. Now that's the second E-stop. And remember, this just wraps around here, and this just wraps around there. And then if we want to reset, do we want automatic reset or do we want push button reset? I guess we could have push button reset on there. There's my reset push button there. And then we'll pass the voltage here. And let's say we're going to turn on a system, and just with a single contactor. Just put K1 right here, a single K1. And then we want to monitor the system, it said. So is this on or off? Well, we got to look at the contacts of it and put it here, K1, to see if it was on or off. And then basically we go to our circuit, our motor circuit, which is right here. There's my motor, and this is my contactor, K1. So maybe something really simple like that would have sufficed. Did you want the PLC to monitor it? Well, then this goes to voltage, and then this goes to my input module, my, I1. If we want to monitor something like that, so we can see what's going on. So that's real basic, kind of simple version of that quiz there. So quizzes were okay. We had a mix here. What people were doing with this right here is they were putting absolutely everything that we went over in class on here. So there was like 10 things on here because they're thinking like, oh, one of these is right. Yeah, I just really wanted the thing that it's asking for. So in today's quiz, just try and give, there's a lot on there. Just give me, what's on there, okay? Hang on one second, I'm doing good here. Yeah. Week 4. So week 4 is, we're talking about data communications. How many nodes does a device net have? What's the advantage of serial parallel? What's token network? The function of a switch in a star network. How are I/O devices mapped in remote I/O? What's the purpose of boot P, and what is it, the network gateway? So a lot of this is just right out of that reading, and I encourage you, your time is valuable to have me put up PowerPoint slides and just read them. The PowerPoint slides, some of this is canned right out of the textbook. I can beat it to death if you want, but I'm just going to try and hit on the high points. I encourage you to just do the reading and understand it mostly out of the book. And if you have any questions, you can directly ask me. I'll try and hit on the high points here, but my advice is, this is all in the book. Okay, this is not in the book. So we have remote I/O, and it says, can both lights be on at the same time? So let's look at this. Push button 5, which is data 4. Push button is data 4. So when this is true, this is false, and when this is true, this is false. They're interlocked. Okay, so at that point, you would think, well, these are interlocked, so either light 1 is on or light 2 is on. I can't have both lights on at the same time because the input is interlocked. Well, the thing is, you can have both lights on at the same time because the input scan and the I/O scan is separate of the ladder scan. Okay, and you're like, wow, that doesn't make any sense to me. Well, in the first part of this lab, what we're going to do is have you do a little I/O mapping, and you're going to push this button, and you're going to figure out how many times you got to push this button to see that both of these lights will be on. And the way that we're going to do that, to see that both of these lights are on, is we're going to put a little counter in there, and we're going to take a look at the data table. So when we take a look at the data table, I just want to be sure you understand what's going on. This is a 16-bit word for the output table because we've got 16 outputs. If the first output, which would be output 0, is on, I'm getting a 1 right here. If I looked at this number right here as a decimal number, this is telling me I have 1, 1. So the value of this word right here is, 0001 is decimal. The value of this is 1. All right. Look at the output table again. In this case, it looks like the second, or the second light. Here the first light was on. Here it looks like the second light is on. Okay. Well, this is the 2s category. See how they keep going 2s, 4s, 8s, 16s, whatever. Well, if I converted this to a decimal, well, I don't have any 1s, but I've got a 2. So the decimal number of this is 2. All right. If for some reason the only light that was on was this one right here, number 7, that's 128. The value would be 128. Look at this last one if I looked at the output module. If I had this light on, and this light on, and this light on, the words 00001011. If I wanted to look at this as decimal, the decimal of this would be 8 plus 2 plus 1. That's 11. This is, in decimals, is 11. That's the way that this looks like. So in this case, if I have the 0 light on and the 1 light on, if I have the 0 light on and the 1 light on, that means I got a 1, 1 right here, which means I've got a 2 and I got a 1. The value would be 3. All right, so take a look at the lab and read that to be sure you understand how we're going to put together a program that will figure out if they're both on. All right, so data communications, I'm going to blast through this. This is out of the book. There's 2 types. There's point-to-point and there's network. The SLIC 500s, what we did point-to-point. We didn't go through any modem or any kind of router. We just plugged the computer into the PLC, okay? Now we're going to be doing network in this class. Transmission media, we talked about this in the prior class. There's coax, twisted pair, fiber optic. We use cable, different types of cabling and everything like this. What we're going to be using now is going to be twisted pair Ethernet connections to connect the controllers together, because we're doing lots of Ethernet here. The industrial networks, this is summarized where, we have our device level. We've been doing a lot with device levels. Ours have been mostly push buttons and lights we've been turning on, but, there's motor starters, any kind of field devices. And you start working up your way to the control level here, to the PLC, to the information level, to where you can share all this data throughout the company if you want. We're not really there. We're just sharing. We can share the information amongst ourselves, but we're not even doing much of that. So we're mostly dealing kind of with this lower control level, and the device level is the industrial networks we're using. Device level, that's your sensors, everything like that. I think everybody feels pretty good about this. We've talked about sourcing and syncing different sensors. You have your local rack that has those static push buttons and lights on there. You're getting around that really well. And then we hooked up some other stuff with the DC modules. It's a little messy. There's leads flying all over, but it looks pretty good. The control level is a level that contains network controllers such as PLCs and robots. So we have a PLC, but we haven't networked them together necessarily. We do have a couple of computers coming into the same network, but the more you add to that control level, the more complicated it gets. And at the very top is information. That's your plant-wide network. Because it's Ethernet, you can share all this data. You can share the data about what's the status of the limit switch with all the way throughout the company. The sales department really wants to know what's going on with that limit switch. They can check it out. Not that they care, but this is where you really get automation to know that we're running low on this inventory. We automatically order some more, or the quality is the PLC is saying the quality is this good or that good, and we can share it with everything. So that is really the network. Okay. Now, when you connect all these together, we talk about a gateway. Okay, a gateway makes communication possible between different architectures. So right now we're staying with Allen Bradley, okay, and we're using data highway. We are doing Allen Bradley Ethernet IP, which is pretty standard, but we are using DeviceNet, which is Allen Bradley. If for some reason we had some Siemens devices or some Modbus devices, we can still get them all to work together and to talk to each other. but you need a bus, all right? So when I think of a bus, I think of a translator. So if you have somebody in the room, you know, from Modbus here, and they speak German, and then you have, or Siemens, they speak German, and somebody else speaks Italian, and then somebody here speaks English. Well, you need a translator, okay? And that's kind of what I think of when I think of a bus, or the gateway to get from the Allen Bradley to the translator, okay? That's the basic format, because the gateway here, you know, how are we connecting? Well, in this case, we're going to be connecting, I guess, with Ethernet. But if it was somehow else, we're connecting RS-232 or something, we need to get this English through the gateway, you know, to RS-232, and same with all these, so that the translator's really understanding it. Okay. IT/OT convergence. What is it? So here's the issue, and maybe we talked about this a little bit. Your IT people, that's your information technology people, they know a lot of stuff about networking. They know a ton of stuff about switches and modems, you know, and setting up, you know, all your IP addresses and everything in your network. But they don't know anything about PLCs or robots or anything like that. Your operational technology, they don't know anything about robots. They're really good with switches. Whereas the operational technology people, they are good with limit switches and variable frequency drives and electric motors and everything like that. But the problem is now all this operational technology is connected via Ethernet. And so the operational technology people can't be calling the IT department all the time to hook up their devices or to troubleshoot their devices, because the IT's got better things to do. You know, they got tracking down viruses, and I don't know what IT people do. They do all the other stuff. So you want to be a hero, it says. Be the guy on the floor, or the guy or girl on the floor that understands all the electric motors and starters and the VFDs, but also understand how the IT works with it to get it all to communicate. That's called IT/OT convergence. And that's what you're typically seeing is the operational technology, the person in charge of that is getting a much more deeper understanding of the IT. Couple of different networks. ScanPort module. This is a ScanPort module. It has 3 channels for point-to-point devices, and so it's just really redundant. So the information you're coming from one to the other is very redundant. We did the SUC 500 where we used either a UIC or a DF1. We didn't use both, and it was only a single channel. ScanPort's got 3, just to be sure. DeviceNet. That's what we're going to do. In this class, it connects remote I/O to a PLC, and it's for Allen Bradley, and I'm not saying it's obsolete, but there's a lot of it out there. So we are going to do some DeviceNet. Here's a typical DeviceNet network. There's a single trunk down here, and then all these devices get plugged into that trunk line, and it's an open device network. It's relatively low speed, but it works good for I/O. All right, so that's the device network that we're doing. We're going to be using a device scanner. It plugs in. It's a card. I'll pull it out, and it gets power, and it does data across the device network, bus network. Okay, so we're going to be able to plug our I/O, and it's going to get across this bus. All right, and so it's got power and data coming through the channel. There's a ton, you know, of information in the packet about the SIP, the Common Industrial Protocol, and it's this communication data is carried over 2 wires, and then a second set of wires carrying the power. So if you look at a DeviceNet connection, there's 5 connections. The other one will just be ground, all right? And that's the Common Industrial Protocol. In PLC 3, we get much more into the Common Industrial Protocol. We're going to use the DeviceNet compact block. So this is in your network. You can, or in your packet, you can take a look at it. Take a look at the connections. Be sure, I should have a resistor needed for termination. There's pins 1, 2, and 4, 5. 2 of the pins are used for communication. 2 are used for power. So it's the information of how this DeviceNet compact block is in there. Take a look at it. And when you're reading the lab, I think you should read the lab because it says reference this this packet or this information that's in the packet. It's not all in the lab. The lab is pushing you out to the packets. Okay. The network nodes, as signals travel down a network cable, they become distorted, and that's called attenuation. You might need a repeater if you have a lot of different nodes. So the DeviceNet that comes in is going to have 64 nodes, okay? And so when we put our compact block device on there, page 5 talks about a node address. It's probably going to be set. When you go in there and you scan it, it's going to find itself on a node. You can have 64 nodes, 0 to 64. It's going to pick one of those. All right. The block IO is going to be set to. So this is just a further way of addressing this, and that's why when I showed you before that there was so much data on that block for the SLC 500. I think it was up to 32. This has 64 nodes with 15 bits on each node, and you'll see when you set it up. Okay. The scanner, the purpose of that scanner when you plug in is it obtains the info. It reads your inputs, it writes your outputs. You can download the configuration. It monitors the operational status. The SLC 500 and CLX scanner, the module will go into the RAG. These are scanners often the first node. You can change it if you want. Do not hot swap these. We are not doing the SLC 500. Once upon a time, I made people do the SLC 500 just for fun. It is so slow. Oh my gosh, getting the SLC 500 to initially scan is just crazy. Okay. And so when you're going to set up this, you're going to be using a program called RS Networks. And here is DeviceNet, RS Networks for DeviceNet. And so when you come in here and you connect, and then you click your little network button right here, it'll ask you how you want to connect. Yours will be, you'll go through and it will be set up to connect through your logics, and you'll find it in here. I don't have anything connected. But then it will go through and it will scan relatively quickly on logics. All right. As soon as you'll see, it's like using RS links. You'll see maybe slot 0, boom, a card will pop up here. And maybe slot 5 or 7 or 8 or whatever, 21, whatever, your remote device will pop up here. Remember, it'll keep scanning all the way to 63. But once you've got your 2 devices here, you can click OK and then continue on to your lab. But this is the software we're using to configure the DeviceNet. It's called RS Networks for DeviceNet. Okay, so another piece of software. The other thing is once you got this all configured and downloaded in the Logix and it's running, Logix remembers it. So later on, you can just download your program into Logix again, and it will bring everything with it. It'll bring that networks with it. Bus topology. This is a slide out of the book. You want to do it. It's where every stations are connected in parallel. So they're sharing a trunk down the middle here. They're sharing a trunk down the middle here. They're in parallel. Okay. RS Networks shows the topology on page 52 that I handed out to you. I encourage you to take a look at all those documents. And so how does this work if they're all in parallel? It uses what's called token passing. A node can transmit data on the network only when it possesses the token. So you get the token, and then you have control of the network. You can send your I/O data, and then you pass the token. And then this person's got the network, and then they can talk, and then they can talk, and then they can talk. So it works relatively fast, token passing network. And it's got built-in error and everything into it. So there's a token passing network. A peer-to-peer network has a distributive means of control. So, and that would be the token passing. Data highway is the Allen Bradley version of this, right? Each device or each node can request the use of the token and take control of the network, but then you pass it on. So there's further explanations in the book. Control net network. So a control net network is a little bit higher level of a network than DeviceNet. Here's our DeviceNet. We got all our devices down here that we're going to be sharing. A control net it's a high speed and it's repeatable. And the thing about the control net network, maybe you'll see them or not, a little bit older. Now that Ethernet's here, it's not going to be used as much, but it's just redundant. There's 2 signals on this control net just to double check all the data that's coming through. DeviceNet, we only had the 2 wires for the signal. So we had the 2 wires for the power, and we had the 2 wires for the signals. All right, you have a control net network. It's not like that scan port that's got 3 ports. It's got 2. So a control net network is a little more sophisticated. Here's my control net redundant media. So notice it's got, use the CIP communications protocol, and notice it's got an A and a B on here. So it's got two different trunks, and each thing's sending two different signals, and it's comparing those to be sure that, in case something gets cut or becomes loose or it's noise. So it's just a redundant media would be my control net. Okay. Once again, jamming through these because these are in the textbook. All this reading is in there. Ethernet IP. So it's IO network plus a computer peer-to-peer network for data sharing. This is really what you're going to see nowadays is your Ethernet IP, and we're going to set up our Ethernet IP remote IO. Okay, and we've been doing just a little bit of this where you are going to have a switch, and so these switches are going to be in a star network. All right, so let's say this is a switch. All these items are starred off of it, and here's the item, and it's starred off of it. Okay, so our switches have 8 ports on them. You can plug in. We're sharing computers, 2 or 3, so that's 3 of them. Ethernet IP you could plug in a variable frequency drive, a stereo drive, whatever. And then if you run out of ports, just take that switch and plug that switch into another switch that's got 8 ports, and you can plug 7 more things into it. So you just create these star networks, and the switches can plug into switches. All right. So your Ethernet is then showing even a higher communication. And it's the common application layer for control device net and Ethernet IP, and they share the common application layer. And you can interchange all of these. So what does that mean? Well, we're going to be using device net, but we are plugged into an Ethernet controller, and we do have an Ethernet bridge and everything like this. So if we wanted to share this between controllers and stuff, we could. All right. So, but Ethernet IP, static IP addresses is really what you're going to see mostly today in today's world, and I think you're going to find all this pretty cool the way that it works. And so the information for this is in your packet. It's using an ANTR is seen as a child configurable rack, and we're seeing OB and IB slots, and as you go through and you set this up, here's some example of some modules right here. And so, over on this side, when you plug this in, that's going to be your, like think of it as like your rack or your controller that you're going to plug in. And then these are the slots that you would put in. So, that's a slot 0. And then, these would then go in, and we're using an input and output. And this one here I don't know, there are 4 to 20 analogs and some DC syncing inputs and outputs. I'm going to give you a rack that, and the instructions will go through. And once again, I've got this all set up with banana jacks, so you can make digital connections to the I/O. Okay, but the instructions for doing that are all there. You just got to be sure that you size the rack correctly. Just like setting up Logix, we're using a 10-slot rack. Don't set up a 4-slot rack because we have a 10-slot rack. You don't set up a 13-slot rack, because we have a 10-slot rack. So same thing when you go in through, you just want to set it up. And when you go and you set it all up, it's going to come into your tree down here. And same thing, when you download and you're running great, these are going to be looking good. If they're not, they're going to have yellow, and it's not going to be seeing them. And the issue is you might not have configured them correctly. Maybe you didn't disable a key. Maybe you didn't match the rack. Maybe you put the input first and not the output. I don't look at the equipment. Look. Just this look at it, and be sure that you're setting it up right. Because even on the first day, we had a couple people mix up the input and the output modules, slot 1 or slot 2 or whatever. Same thing here. If you mix them up, it's going to be a problem. But these are seen as children in the configurable slot. The lab walks you through it. Here's the network topology of the star. So we're going to be the switch here. And these are the different devices, whether it's your computer or whether it's the Ethernet I/O or PowerFlex drives or whatever. They just come into your switch hub called a star network, right? Page 34 shows your 1734.io manual, shows you how to set that up. Okay. And that's what we're talking about is our local area network, our LAN that puts them together, we're running through that static switch. And the thing to know here is that this does not use token sharing, it uses a collision detect. Nodes listen for activity on the network and transmit only if there are no other messages on the network. So this works really fast. If they don't hear anything, they send something. But if two things send at the same time and they run into each other, the collision is detected, and then they will resend the data. And it all works, very fast to work on the collision detect network. This is right out of the book, as you can see. You can read it, take a look at it. Ethernet IP. Page 27 shows you how to do this. If I give you a unit that's new out of the box, you have to use the boot PDHC to set it up with a static IP address. The ones that I'm giving you should be set up. So if you go into your links, and you go to Who Active, and you go into your links and your Ethernet and everything like that, it should pop up with a static IP address, assuming that you don't have something on the same, two at the same address. So don't be punching on the toggle wheels to change the IP address on them. Let me know if you're having problems getting. No, I shouldn't click that. If you're having problems getting that, okay? A couple of other quick hitters. Some of the other networks that you might see out there are Modbus. You might have heard of Modbus. It's still out there. It's a serial communications protocol, and it used to kind of led the industry standard once upon a time. As I mentioned, nowadays, Ethernet IP is going to be the big thing, but it's serial communication open protocol. Find this on Siemens or Modicons, okay? It's just some background information is available in the textbook. Fieldbus, you might see some Fieldbus. It's a serial communications for measurement and control equipment. It's older, so you might see some Fieldbus stuff out there. Open two-way communications using daisy chain. Nowadays, like I said, probably going to see a lot of Ethernet IP, but there's still Fieldbus out there. And so, my quick summary for these kind of things: scan port, Modbus, Fieldbus. If you run into this and you got to service some equipment on this, at that time you can go to the seminar to learn, exactly how to do this, or you guys are smart people. You can download the 1,000-page manual and read it yourself, and then get yourself up to speed on this. I'm just making you aware that these are some of the other things. You might be quizzed on them, so you want to take a look at just the reading about what that is. All right, so I kind of crash course through the items, like through the communications, like I said, because I don't want to waste your time. It's in the textbook, it's in the reading. I tried to hit on the high points. The quiz, you might need some restarts because we're going to be doing a lot of passing of data and everything, and sometimes the studio gets a little bit messed up. We've had some people where logic stopped working and was doing something weird we don't understand. You save your program, you restart logic, and it works perfectly fine. If that doesn't work, you might have to restart the computer, okay? So we're doing device net, and then we're going to do Ethernet IP. The produced and consumed tags at the end, I don't even know if this is extra credit. We're not going to do that. FYI, Part E. Today's your lucky day. I moved that to PLC 3. So no produced and consumed tags. But this stuff, just getting through the instructions, just reading all the manuals is going to take a long time. So the more you can kind of prepare yourself and understand what's going on ahead of time is good. But really, this is a kind of intensive setup of these devices is going to take a while, okay? And luckily, we're not doing the Slick 500 device net because that is a really slow read on that, okay? So that was it. There's a quiz out there for you. Good luck, and I will see you all soon.